Chapter 3 is all about polynomials, and we're going to start with section 3-1. One of the big things about polynomials that we'll be using a lot is the degree, which is the largest exponent of x. In the first example, they're going to ask you to find the degree of the polynomial. And so I said it's the largest exponent of x, so we would say that the degree of this polynomial is equal to 4. We also have a leading term, so this would be our leading term. So it's the whole thing with the numbers and the x's. And last but not least, we have the constant term. So the constant is the number that doesn't have an x. So in the next example, I'm going to have you find the degree of each of the polynomials that I give you. So basically, you just need to look at the largest power of x. So the largest power would be x to the first, so that you would say the degree is 1 for this polynomial. So for this one, it's x cubed minus 5x to the 7th. This isn't written in standard form, meaning the largest isn't first, but the largest power is x to the 7th, so you'd say the degree of this guy is 7. And this last one is a little bit tricky when it's f of x equals 5. There's no x term. This is the same thing as x to the 0, because anything to the 0 is 1. So we would actually say that the degree of this polynomial is 0. So the next thing we're going to be talking about is end behaviors of polynomials, how they end. So if you notice all of the exponents, the red graph is x squared, the blue graph is x to the 4th, green x to the 6th, purple x to the 8th. All the exponents are even here. So whenever you have even exponents, notice how they all end. They all end in the same direction. Here I have all odd exponents. So x to the 1st, x to the 3rd, 5th, and 7th. So these are all odd exponents. Notice how all the odd graphs end in opposite directions. So one ends on the positive side, one ends on the negative side. So we're going to be talking about the end behavior of polynomials, and basically what that describes is what happens at the endpoints of a graph. So we're going to be looking at the odd degrees, the ones that ended in the opposite directions, and even degrees. So let's start off with odd degrees. So we're going to have positive leading coefficients and negative leading coefficients. And here's what a graph would look like if you had a positive leading coefficient. So let's pick like x cubed, or something to the 3rd power. It has 3 directions. We'll talk about this in a little bit. And if you have a positive leading coefficient, what happens is that the end behavior, it ends up going positive on the right-hand side. So one thing to remember is you read a graph from left to right. So if it has a positive leading coefficient, it will end up going positive on the right side. A new notation is this. You're going to be writing this as x gets bigger, or as x approaches infinity, that little arrow means approaches, our y values also approach positive infinity. So as our x values get bigger, so do our y values. If I were to look at the end behavior on the left side, I'd say as x approaches negative infinity, so as our x's get negative, our y values also go negative. So y also approaches negative infinity. If you have a negative leading coefficient and it's odd degree, remember odd degree means they end up in opposite directions, what will happen is your graph will look something similar to this. It ends up going negative on the right-hand side. So if you have a negative leading coefficient, it ends up going negative on the right side. So you're only looking at the right side. So how you would state this is as x gets bigger, so as x approaches infinity, here's your x values, your y values are actually approaching negative infinity. If you were to read the behavior on the other side, we'd say as x approaches negative infinity, so now we're looking at the negative x values, our y values would actually approach positive infinity. Now let's look at even degree polynomial functions. So when something's even, if you remember all those even powers, they ended up going in the same direction. So I'll do a graph that kind of looks like a W. This is even because they end up going in the same direction. Whenever you have a positive leading coefficient, you look at the right side of the graph and notice it's going in the ending in the positive direction. So if I were to do the same notation as before, I'd say as x approaches positive infinity, as my x's get bigger, so do my y values. My y's also approach positive infinity. You can put the positive sign if you like, or just leave it as infinity. Here on the left side, I'd say as x approaches negative infinity, so as my x's go negative, my graph goes positive. So the y values approach positive infinity. If I have a negative leading coefficient and I still have an even powered graph, this time my graph will end up opening downward. So looking on the right hand side, if I have a negative leading coefficient, it ends up going negative on the right hand side. So as x approaches infinity, my y values would actually go to negative infinity. As x approaches negative infinity over here, my y values also approach negative infinity because they're going downward. So before I give you an example on determining end behavior, I want to review a concept from Algebra 3. If you have a degree 3 polynomial, there is 3 directions on your graph. So here's what I mean by that. You have 1, 2, 3 directions. So this would be a degree 3 polynomial. If I have a parabola, which is x squared, you'd go, oh duh, that's degree 2. Well, on the graph, you'd notice that you have 1, 2 directions. That's why it's degree 2. So this graph right here, I know it's going to be odd because they end in opposite directions. So is it 3, 5, 7? What is it? So you just have to count the number of directions. So I have 1, 2, 3, 4, 5. So the degree is 5. The other thing is if I have a polynomial that looks like this, you could tell me 2 things about it. You could tell me that the degree, if I draw it, is 1, 2, 3, 4 directions. You could also tell me because it ends up going negative on the right side, it has a negative leading coefficient, what we just talked about. This also has a negative leading coefficient because it's going down on the right-hand side. These guys here both have a positive leading coefficient because they end up going positive on the right side. Okay, so now for an example. So I want you to determine the end behavior of this polynomial, 8x cubed minus 7x squared plus 3x plus 7. Alright, first thing you need to know is the degree, because that's going to tell you how to draw it. And we're going to do this all without a calculator. So the degree is 3. We also notice that the leading coefficient is positive. So I'm going to put positive leading coefficient. Alright, so now what we're going to do is, since it's degree 3, we have 2 options. It's either going to look like this, 1, 2, 3, or it's going to look like this, 1, 2, 3. You've got to figure out from the leading coefficient which graph it's going to be. Because this is positive, we know it's going to end up going positive on the right. So this is going to be our graph. So then we just have to state the end behavior of that graph. And this is just kind of a generic graph, but all we need is the end behavior. So as x gets bigger, or as x approaches infinity, our y values also approach infinity. As x approaches negative infinity, our y values approach negative infinity. And that would describe the end behavior. So in this example, we know that the degree is 4 because it's the largest exponent. And our leading coefficient is actually negative. So when we draw our graph, we have 1, 2, 3, 4 directions it would look like that, or 1, 2, 3, 4. Which type of graph is it going to be to state the end behavior? Well, because it's negative, we know that it's going to be this graph. So that means that we are going to state the end behavior for this. So as x approaches infinity, so as x gets bigger, our y values get smaller. as x goes to negative infinity, our y values also approach negative infinity. Okay, so this completes part 1 of the notes. We're going to talk about shapes of zeros in the next segment, so go ahead and click on that video now. So finishing off the notes for section 3-1, we're going to be looking at repeated zeros and also what the shapes of the graphs look like near those zeros. So the main thing is looking at what it looks like at the zero. A zero also is known as an x-intercept. So in this first example, the first thing you're going to be asked to do is find the zeros. And the zeros are the x-intercepts. So I have zeros here, here, and here. There's 3 zeros. So I would say one of the zeros would be at x equals negative 2. I'd have one of the zeros at x equals 0. And then I'd have another 0 at x equals 3. So if you look at the original expression right here, if I set each of these factors equal to 0, I could go ahead and get each of the solutions that I have right here. The one thing that you might notice is this one, this 0, it's twice. It's x minus 3 and then it's a factor 2 times. Notice what it looks like at 3. If you have a squared, it kind of bounces off at that 0 right there. It kind of looks like a parabola. What's the degree of this polynomial? Well, all you have to do is multiply all the x's together. So this would be x squared times another x would be x cubed times another x would be x to the 4th. So this is a degree 4 polynomial. Also notice how many directions it has. 1, 2, 3, and 4. You can also look at it that way. So the main thing is it looks like a parabola at the 0 where you have the squared. The other ones, they just slice through and there's just 1 there. In this next example, we have x times x plus 2 times x minus 3 cubed. First thing, what are the zeros? So you can set each of these factors equal to 0. And you would get x equals 0. You would get x equals negative 2, and you get x equals 3. Notice the graph. Here's negative 2, here's 0, and here's positive 3 right here. So notice what happens at the one that's to the 3rd power. It kind of looks like a cubic. So it slices through. It doesn't bounce or look like a quadratic when it was to the 4th, but it slices through and looks kind of like a cube. The ones that all have one factor just slice through like this, and then don't bounce off or bend at the 0. And in this example, we have each of our zeros at x equals 1 right here, and we have negative 2 right here. And if you were to set each of these equal to 0 right here and here, you could get 1 and negative 2, the 0 straight from the graph. The degree, all you do is add the exponents. The degree is 7. And here's the big thing, is notice when it's cubed, what happens at the 0. At 1, it looks like a cube. And then when it's an even power, what it does is it bounces off. This is a little bit flatter, because to the 4th power looks like this. So x to the 4th kind of looks flatter. Not really like a parabola, but flatter than a parabola. So then it bounces off and kind of looks like a 4th power at that root. So we're going to summarize our findings that we just came up with. So we're going to talk about the shape of a graph near a 0 with a repeated factor. So starting off, we're going to talk about if it's an odd power. Alright, so if m, which is our exponent right here, is an odd power, meaning 1, 3, 5, 7, or so on, what's going to happen is our graph will slice through at positive c, because positive c is what will make that 0. And if it's 3, 5, 7, it will either bend like that, or, let's say this is c, it can bend this way. In either case, it slices through the 0. So in case 2, if the exponent is even, so let's say my factor is x minus c to the m power. So here's your exponent right here. So if you have 2, 4, 6, 8, and so on, when you go ahead and make your graph, what's going to happen is at positive c now, what makes that 0, your graph is going to bounce, and it'll either be flatter depending on the power, but it'll basically bounce off of the 0 and not slice through. So it either can be on that side of C depending on the orientation, or it can bounce like this, but it will not go completely through that 0. So now that we have all the tools to actually graph, we're going to be graphing polynomials with, sorry about that, that was my water bottle. We're going to be graphing polynomials without a calculator, and here are the 3 steps. Step 1 is to find the zeros. Step 2 is to use the leading coefficient to determine the end behavior of the graph. So is it ending up on the right or down on the right side? So the last step is to determine the shape of the graph from its degree. So if it's degree 4, you'll have 4 turns or 4 directions, along with how the graph bends or bounces off the x-axis at the repeated zeros. So remember, if it was an even degree, it would bounce off, and then if it was an odd, it would slice through but kind of bend at the 0. So in this example, you're asked to sketch a graph of p of x equals x minus 1 squared. So notice that it's squared, so we're going to have a little bounce on the x-axis, x minus 2, and x minus 5 cubed, and this one's odd. So first thing you have to do is determine the degree. So remember, if you were to multiply all this out, you'd have an x cubed. You get the x cubed from that times this other x, so now we have x to the 4th times another x squared because that's squared. So basically just add up all the exponents. You get 2, 3, 4, 5, 6. So it looks like we have the degree is 6. So if I were to do a little sketch over here, I would have either something that looks like this, 1, 2, 3, 4, 5, 6, or I would have something that looked like this, 1, 2, 3, 4, 5, 6. I just have to figure out which one is going to be the right orientation. And what we do is we look out in front. So in this case, notice how I have no negative out in front. It's positive. So that means it's going to end up going positive on the right. And then the last thing I have to do is look at the zeros. So let's go ahead and find the zeros next. Alright, so I'm going to go ahead and set each of these factors equal to 0. So I'm going to have a 0 at 1, I'm going to have a 0 at 2, and I'm also going to have a 0 at 5. So I'm going to make a little note right here. The 1 at 5 is a triple 0. And the 1 at 2, or the 1 at 1 is a double 0. So I'm going to put double. So anything that's even is going to look like this at the 0, and anything that's odd is going to look like this at the 0. So then I'm going to go ahead and make my sketch now. So I'm going to mark down my x-intercepts or my zeros, 1, 2, 3, 4, and 5. And then I'm going to put my little marks on it because this is where it's going to cross, 1, 2, and 5. And then I have to make it look something similar to this. It's got to have 5 directions. So at 1, it's going to be a double direction. Now I actually like to work backwards because I know it's going to be ending up. So at 5, I have to make it look like this. It's going to be a triple. So I'm going to do this. Alright, so that counts as 1, 2, 3 directions. And notice how I'm ending up going upward. And then at 2, it is a odd degree, so it's going to slice through. And then at 1, it's going to turn and bend and go up something like this because of the double 0. Anytime it's a single, it slices through. And then if it's 3, 5, 7, or larger, it's going to bend at the 0. So that would be my graph. In this example, first thing we're going to do is to determine the degree. So adding up the number of x's, you have an x squared here times another x, so it's x cubed, or the degree would be 3. Next thing is the orientation. Notice that it's negative. So that means if I have a negative orientation, that it's going to end up going left and have 3 directions. So I know it's going to end up going down on the right-hand side. So it's going to go down. And then the zeros are what make each factor equal to 0. So I have one at -3 and +3. And the one at -3 is a double 0 because of that little squared on it. So that means whenever it's double, it's going to bounce off the 0. So now I can go ahead and make my sketch. So I'm going to put -3 and +3 right here. I'm going to go ahead and put on my marks. Use a different color here. And then I know that it has to go down on the right because of this negative sign, and it has to have 3 directions, and then it has to bounce at -3. So I am going to work backwards. I know it has to end up going down. This one right here is a single 0, so it's just going to slice through, and then it has to bounce off of that one, and then it looks like that. So anytime it's a single 0, there's just one, it slices through. Anytime it's a double or a quadruple, so 2, 4, 6, it'll bounce. And then if it's like 3, 5, or 7, it will kind of bend at the 0. So the last thing is the local extrema of the polynomials, and we've already done this. These are just the local minima and maxima of the graph. So if I were to do a little sketch, and let's say your polynomial was degree 3, you would have your local max, and this would be your local minima. We've already done this in the last 2 chapters. So there is one theorem, and the theorem states if p of x is degree n, then there is at most n minus 1 local extrema. So basically in the example I drew here, we have the degree 1, 2, and 3. That means there's 1 less than 3, or 2, 1, 2 local extrema. So in this example, you're supposed to determine the number of local extrema of this polynomial. So the big thing is you need to know what the degree is. It's the highest exponent, so the degree is 4. So you know there's at most 1 less than the degree. So there's at most 3 local extrema. Now to figure out exactly what they are, you'd need to create a graph. So in this graph, you'll notice that you have a local min here, a local max there, and another local min. So there's your 3. So then to get more specific, you would say 2 mins and 1 max. And to calculate them, they didn't ask you to calculate them. You could just do calc min and max and look at the y coordinate. Okay, that's it, and I will see you guys tomorrow.